So we start now. The next session of the workshop. So this is an European session. So now we start with Italy, Milan, and the Munich. Then I have a remote presentation. So let's start with this Nubes object-oriented programming for stateful serverless function, and Luca, next.
Hi, yeah, I'll be presenting our work, which is titled Nubes, object-oriented programming for stateful serverless functions. The main author, Kinga, could not be here, so I'll be presenting, and I hope I can answer all your questions. So where are we as a work? We work in the context of functions as a service, which you may know from providers such as AWS Lambda, Azure Functions, or Google Cloud Functions. Why do we use them? What are the advantages? The advantages of serverless functions is that you don't need to manage servers. You have automated scaling on demand, and the pricing is based on the actual resource usage. Usually, how is a function as a service structured? Well, we have client programs which make requests to functions that are hosted in a cloud environment. These functions are automatically instantiated by the provider, and they are fundamentally stateless. So what do we do if we need to manage some state? Well, we interact with that database. And what does this mean? This means that we have stateless functions that must interact with an external storage solution, such as a database, which can also be provided as a service. What is the problem? The problem is that developers need to write the code for interactions between the application logic and the storage. This means that while we gain in simplicity, because we do not need to handle the deployment, we lose in the sense that we increase the complexity of interaction with the storage, as we need to manually manage the state and interact with the storage servers. So this slows down the development process and hampers the modularity and reuse, since all these interactions with state are written in the code and are not implicit in the structure we use. What is Nubes? So Nubes is a novel programming model for stateful serverless functions. What is the goal? The goal is to accelerate the development process and introduce a low overhead in terms of latency. What is the structure of a Nubes program? Well, we take inspiration from the object-oriented paradigm, and we work with objects. Objects have methods, which are functionality, functions, and state, which is data that can be persisted and stored across invocations. How do we do that? Well, in Nubes, we have object types. The types can have fields, which are data. In this case, you can see an user with an email, password, and name. And objects have associated methods. These methods correspond to functions in the functions as service paradigm. We use one table for each type of object, and we store the fields in a database as a service. In our demonstration, we use Go as a language and AWS DynamoDB as a storage, but this could be changed. It's not fixed in the programming model. So as I said, we map the fields to the storage servers and service, and we have functions for the methods. What does Nubes do? Nubes uses code translation and generation to automatically manage the interaction with storage between objects, and also within methods of the same object. It generates a client library, which clients can use to interact with the objects that are deployed in the cloud environment, and deployment files that can be used to actually deploy the application. So we define objects as in our reference implementation, we are using Go, and we have a struct that can have an ID, and we have methods of the struct. These methods are automatically converted into serverless functions with the state interactions handled automatically. We can use we can use Go tags to annotate some fields, to demark some additional characteristics. In this example, we have an ID as an email. The objects, what is the life cycle of an object? An object starts from being uninitialized and then can be exported to the storage. Then it is considered initialized. Also, an object can be loaded from the storage or deleted. Nubes supports relationship. It has many-to-many, one-to-one, and one-to-many relationship, both single and bidirectional. This is achieved by simply annotating the fields, as you can see here. We evaluated Nubes comparing with the standard methodology for stateful serverless applications, aiming to answer two questions. Are the applications developed with Nubes simpler? And does the overhead introduce, is the overhead introduced significant or not? So the experimental setup, we compare Nubes with two implementations. We demark SSF with a traditional approach using a normalized storage structure, and SSF custom as the same approach, traditional, but using an optimized storage schema. We use use cases derived from the DevStar bench, which is an open source benchmark suite from microservices applications. So when evaluating the effectiveness of the programming model, we see that with Nubes, we don't have to manage the storage initialization, read and write to the storage, and serverless function handlers. And we see that we only need to write 368 lines of code manually, with 600 being generated, compared to the traditional approach, which required 1,000 lines of code. So are they actually simpler? Well, Nubes reduces the amount of lines of code to be written, as well as its complexity, since we don't need to manage the complex state interactions. Also, it enables a rapid migration to different cloud environments in the future, because we just need to add a new implementation for Nubes, and you do not need to adapt your application. As for the performance evaluation, we test the hotel scenario. You can see the numbers of the objects that we used. And as a performance metric, we evaluate the execution time of the serverless functions. And we also measure the latency. The results of the three workloads configuration are nearly identical. On average, the overhead introduced by Nubes within 10% of the median duration of the SSF baseline. And the maximum overhead we measured is about 23% of the median with respect to the SSF custom system. The mean overhead, considering all tasks with respect to SSF custom, is below 15%. So do we introduce a significant performance overhead? Well, Nubes is a general framework, thus it cannot provide custom task-specific optimization. However, with this kind of optimization may bring advantages, but they are less general and less reusable. However, developers may adopt Nubes to speed up the development process and then manually optimize only the required parts, if any. So, in conclusion, Nubes promotes the modularity, reusability through the usage of object-oriented programming concept. It accelerates and simplifies the development process, and the overhead that is introduced with respect to custom implementation, the sacrifice generality and usability is small, while preserving the scalability of serverless solutions. In the future, we plan to extend Nubes with mechanisms that synchronize concurrent access to the object state. So are there any questions?
Thank you for the talk. There are many frameworks that are using the actor model, right, to provide stateful computation, like GreenCourier is one example of them. So how is your object-oriented stateful method compared to Sense?
Okay, so we are not explicitly, we are not exposing an API like actors as an example. What we do is that we allow developers to write their application as if it were a simple traditional application using Go code and traditional Go structs. You do not need to think about message boxes like you would do for actors. You just write the application as if it were normal, and then we use code generation and compilation to actually translate the code and insert automatically the interaction with storage. So it's not the same programming model. Yep. Yeah, okay. As of right now, we don't have, like, we are eventually consistent. We don't have explicit synchronization primitives. What we're working on is on locking primitives. First of all, locking single objects so that you can ensure that no concurrent operation that are conflicting on the state can happen at the same time. And what we evaluated is that if we do something like this, we may use an object that can act as a transaction manager, and that allows patterns for more complex synchronization, where we are still working on that. You mentioned that there are that kind of not be that's interesting. From what, like, the main difference that I see from that and our approach is that what they're doing is something akin to continuations. Like, they actually save the state of the code and to resume execution. What we're doing is not exactly that, because we are separating basically the state and the server and the state part and the stateless part, while that is for resuming the computation. So yeah, there are things that we could like learn from that, but it's not the same thing.
Thanks a lot. So thanks.
Thank you.
So what do I have to do? Okay. All right. Hello. Good evening, everyone. My name is Mohak Chadha. I'm a final year PhD candidate at TU Munich, and this is a WoSC 2023 talk on the topic GreenCourier carbon-aware scheduling for serverless functions. So a bit about who we are. We are the chair of computer architecture and power systems at TU Munich. So this is us at Waldhausschlag, which is a monastery at in the border of Munich, at the border of Germany and Austria. So we work in a wide variety of domains such as HPC, cloud computing, quantum computing, and edge computing. So if you are interested in any of these areas, please feel free to reach out to us. So today's talk will be a bit about serverless computing. What are the challenges in sustainable serverless computing? Then I'll talk about GreenCourier evaluation, and finally conclude the presentation. So looking back at the brief history of the cloud, from bare metal servers to infrastructure as a service, platform as a service, and then serverless computing, aka function as a service, in which users are only responsible for implementing fine-grained pieces of code called functions and deploying them onto a function as a service platform, while all responsibilities around infrastructure management is automatically handled by the cloud provider. If you look at some prominent examples of fast platforms today, right? So AWS Lambda, Google Cloud Functions, Azure Functions, and IBM Cloud Functions. And typically, these cloud providers receive around 1.1 billion function invocations each day. If you look at some of the challenges in sustainable serverless computing, one of the challenges is that due to significant level of abstraction provided by the fast computing model, the core new technologies that enable it consume significantly more amount of energy as compared to conventional technologies. For instance, Firecracker, which is a lightweight micro VM used in production in AWS Lambda and AWS Fargate, consumes 19 joule of energy per function invocation request. Another challenge is that the geographical region or data center for serverless function deployment is pre-selected in all commercial fast offerings. As a result, the varying carbon intensities, that is grams of CO2 emitted per kilowatt hour of energy produced for the different geographical regions, is not considered for function execution. To address these challenges, we implement and propose GreenCourier, a scheduling framework that intelligently schedules serverless functions across geographically distributed Kubernetes clusters to minimize carbon emissions for function execution at runtime. So it builds on Kubernetes, which is the de facto platform of container orchestration in the cloud, and Knative, which is used in production in Google Cloud Function and Google Cloud Run. Right, so GreenCourier consists of three main entities: users, the central control plane, and the geographically distributed independent provider Kubernetes clusters. For connecting the independent provider clusters to the management cluster, we use the open source project called Lico, which is a CNCF sandbox project, which internally utilizes virtual kubelet. So virtual kubelet cloaks a provider cluster as a virtual node and connects it to the management cluster. Using our framework is significantly straightforward. In the first step, users implement functions in different programming languages such as Go, Python, Node.js, or Java, and change the scheduler name in the YAML specification file and deploy them onto our management cluster. Following this, our custom scoring plugin for Kubernetes implemented using the Kubernetes scheduler API scores the different geographically distributed provider clusters depending upon the region's current carbon efficiency. To obtain carbon-related information about the different geographical regions, we implemented a matrix server that currently supports two marginal operating emission rate sources of the local electricity grid, such as which are watt time and carbon aware SDK. So our matrix server is quite modular, can be extended to support other sources, and currently it just provides a REST API, which can be used by the scheduling plugin for scheduling the different nodes. So after obtaining the carbon efficiency scores, our scheduler assigns the function pod to the geographically located cluster with the highest current carbon score or efficiency. And finally, after completion of the binding cycle, the function then can be easily invoked by the user. So moving on to some results, we tested our framework on GKE with Knative for multiple geographically distributed clusters spread across Europe. We use several serverless functions performing different tasks, such as CNN inferencing and LU decomposition. For emulating actual user behavior, we use production open source Azure function traces for generating requests. And we compared our strategies with two other approaches, the default scheduling strategy in Kubernetes and a geo-aware scheduling strategy that maximizes the placement of functions in regions which are closest to the management control plane. All right, so for evaluation, we use the different metrics: carbon emissions, function response times, and scheduling latency and binding latency. So the last two metrics are Kubernetes specific. Scheduling latency represents the time between the node assigned event generated by the Kubernetes scheduler and the pod creation event generated by the replica set controller. Binding latency represents the time between the node assigned event and the pod running event generated by Lico or kubelet in the particular use case. So to quantify carbon emissions for serverless functions, we use the software carbon intensity specification, which was developed by the Green Software Foundation. So the SCF on application is given by the following equation. E represents the energy consumed by the application. I represents the geographical location-based marginal carbon intensity. M represents the embodied carbon emissions, and R represents the function unit of the application. For instance, the number of requests per second. So if you want to learn more about SCI, you can actually scan this QR code. And also you can talk to me after the talk. So moving on to some results. With our strategy across all serverless functions, we observed 8.7% average reductions in carbon emissions as compared to the default default scheduling strategy, and 17.8% as compared to the geo-aware scheduling strategy. But there are also some trade-offs involved. So as compared to the default scheduling strategy, we observed 10.26% GM average slowdown in response time, and also 16.24% GM slowdown, right? So the major reason for the bad performance with respect to the geo-aware strategy is that the most carbon efficient region in our experimental setup, that is Spain and France, are actually the farthest away from a management cluster in Frankfurt, leading to higher response times. Right. So if you look at the scheduling latency, we observe that with GreenCourier, the scheduler takes around 539 milliseconds per pod for assigning to the pod to the most carbon efficient provider cluster, as compared to like 515 milliseconds per pod by the default scheduler. And if you look at binding latency, we observe that with GreenCourier, it's 8.828 seconds per pod as compared to 4.53 seconds per pod with kubelet. So this is basically because, with Luca, you have a lot of additional synchronization because of virtual kubelet. And also you have to communicate over Ethernet as compared to the default setup with kubelet, where all communication is within a VPC. So in the future, what we want to do is make this management cluster highly available and disaggregate it. Also work at the LECO level to improve response times and status synchronization so that the binding latency is kind of reduced. Right, thank you. And I would be happy to take questions if there are any.
Some questions?
Hi, great talk. So Apple has this clean energy initiative where it sort of forecasts when clean energy is available, or like energy from renewable sources available, and it is scheduled like iPhone charging or whatever devices that you charge to the time when that clean energy is available. So I was wondering if anything like that, any forecasting of some sort would be useful.
Definitely, I think forecasts can help, but with serverless functions, since they are really short-lived, and so at runtime it also works. But I mean, if you think that similar to how people use it for cold start, right? So if you are expecting a lot of traffic, you pre-warm some instance so the response time are reduced, then you can also think about that. So if you have a large amount of clean energy in a particular place and you know that there will be a lot of requests, then you can pre-schedule those functions and that region would also work. But then it would also depend upon at that point of, so you can do that actually, it would work. But in this case, we only work on runtime, right? Yes.
I would ask one question.
Yes.
In function service, I mean, you are measuring the computing part, but it makes sense a lot for the carbon part to measure the data transfer to object storage. So have you considered to include in your calculations really the data transfers from object storage to functions?
That's a really good question, and it's really hard to quantify network transfer and energy cost based of that. So in this study, we only focused on runtime energy emissions or carbon emissions, and so I also don't have a great idea how that would exactly work. So I'm still searching for some source which through which that can be done, right? But in terms of egress, if you think about egress and response times, what I've talked to people and what I've heard that emissions or energy consumption related to only egress transfer, that is not much. So the most amount of what is impactful is CPU based or what is running. That's from what I have talked to people and what they've said to me. Yeah, but that's a really good question. It's really hard to quantify that currently. Yes. Close. Close it. Close it. Okay. Right. Don't know, like 9 minutes, I think. Yeah.
Hello, I did not hear you, sorry.
So how much is the award for like the normal presentation in a way? How much do you get? 20 minutes or 20? Oh, okay.
Okay, can you see the screen? Can you hear me?
Yes.
Yes, okay. Okay, so hello everyone. I'm glad to be here today, and I'm going to talk about GIRAFF, which stands for Reverse Auction-Based Placement for Fog Functions. And so I'll first start by giving a bit of context around what is the fog and what kind of function I'm referring here, and the rest is just the usual stuff. So about the fog, well, the best illustration is actually to use a case study. So here is a volcano case study where we want to monitor a volcano with different IoT sensors. So we're talking about like 300 sensors around this particular volcano on an island. And in the sensors, we have ground sound sensors, cameras, and stuff like this. So in 2023, the current ways of doing things is to take and collect all this data and send it directly to the cloud. And you can see that if we do this, first, we use a lot of bandwidth for really not that much value, because most of the time the sensors will just detect pretty much nothing really unusual. And we also do not allow for fast responses and fast recalibration, for instance, of our sensors. So the idea is to introduce the concept of the fog, which is to put computing power in between the data producers and the data consumption in the cloud. So we introduce actually small computers such as single board computers like the Raspberry Pi, or even the use of already available enterprise servers, like small servers in small enterprises in most of the cities of the world. So the idea is that we now are able to run small applications that could, for instance, pre-process the data, and thus reduce the bandwidth usage by compressing or filtering the information. Additionally, we can also take decision locally, for instance, to recalibrate our sensor if we find something interesting without having to run this part of the code in the cloud far away. However, we cannot really do this without any constraint. The first one being that we are using really constrained devices. And the second one is that we are using really heterogeneous devices with some with accelerators, some with a different architecture than what we are used to. And so we have to deal with this. Additionally, we also have to deal with the way we execute our one application on the fog. And so we could pretty much do like in the cloud, that being take a whole fog node and run a whole application, that being a monolith or just a part of the microservice. But this will underutilize the potential of the fog. So instead, I'm pretty sure you're familiar with serverless and especially functional service. And so the idea is to pretty much keep the part of the application that is cloud dependent in the cloud, and the rest of the application divide it into smaller units that we call functions. And one of the main benefits of functions is that when there is no need to run them, when there is no data at the input, we do not really need to run them. So we can save on computing power, and thus we can also collocate multiple functions on the same node. Thus we can increase the utility of each fog node. However, we still have one problem remaining, which is to understand how to place our functions on this really distributed system. And so we have to take into account the CPU and the RAM, which are the usual suspects here. But we also have to take into account the latency, which is the time before the time in between the emission, for instance, from an IoT sensor and its reception in the fog node. And so this is characterized, and we need to take this into account. Another problem is that if we want a big fog network, we have to actually allow multiple providers to be interested in joining our network, and thus we have to incentivize them. And one of the best way to incentivize people is to use money. And so this is exactly what we are proposing in this paper, is to use auctions to incentivize the providers to come and sell their resources and to participate into the network. In order to do this, we actually host the auction in what we call the marketplace, which is a central software which is trusted by everyone and handles all the money exchanging and stuff like this. It's also the proxy between the client that wants to provision function and the different nodes where the function will run. Here the client is impersonated by the client representative, sorry, which executes the policy of when to provision function, when to request a new function, when to unprovision a function, etc., etc. So if we go back to our use case, here we have one sensor that has detected an anomaly on our volcano, and thus the function that processes the data will forward this message because it's an important data, and thus the client representative will know that it now needs to deploy a new function to actually process and collect the data from all the sensors around this volcano, so hundreds of sensors, process the data and find the location of this anomaly. We do this because we want to send a drone and inspect the anomaly in real time. So in order to do this, the client representative will issue something that we call the SLA, which is the service level agreement. This is a simple contract in which we describe the RAM, CPU, and latency requirements of a function. Then this contract is sent through the marketplace to the ideal fog node, where then it's propagated until the latency constraint breaks, and it's propagated to other neighboring fog nodes. So then each fog node will be able to place a bid on this SLA. So the bid will be just the value of what the node expects the function to cost when it runs. And each bid will then be collected and back to the marketplace, where we will hold the auction, find a winner. Then the client will pay the provider, and the function will be executed on the winning node. Then the function will just do its job, like collecting all the data, processing, and then we will be able to send the drone to the correct location and guide it in real time, because the function will be located near the drone, actually, geographically near it. So if we go back to GIRAFF, we provide two main contributions at this stage of the paper, which are that the first one is that we provide an SLA-based placement method for functional service applications in the fog. And I emphasize on the fact that we provide a strong quality of service guarantees, especially on the latency part of the things. And the second contribution is that we try to find a way to incentivize multiple providers to collaborate in the same fog network to make it bigger. Of course, the fog is simply an extension of the cloud, so we try to reuse as much as we can the same technologies. So I'm talking about containers, Kubernetes, OpenFaaS. And because we want to implement it in real life, we need a scaled-up test bed. So we will use the French Grid 5000 test bed to do this. And because we are dealing with a large...
Dominic was using that.
Yeah?
Because of Professor Schreiber.
Sorry. I cannot really hear anything. Should I keep going, or is there... Hello?
Yes, go ahead.
Okay, so I'll keep going. Just okay. So to manage all this and make it reproducible, we use Nix to simplify our life. So here is an overview of our experimental setup where you can find most of what I just described earlier, which is that we submit SLAs at random intervals to the marketplace where we hold the auction and we provision the functions. And of course, we measure and load test every aspect of the functions that we instantiate. So this gives us this first slide of results, which is about to show that GIRAFF is actually as good as two other baselines, or at least as good as the best performing baseline. On the left-hand side, we can see the ratio of placed function, so the number of functions that we managed to place successfully. And we can see that GIRAFF is similar to the two other baselines. The story is a bit different on the right-hand side, which measures the number of times the SLA was respected. And here we can see that we perform as good as the best performing baseline. In terms of economics, we can see that this is quite a win for GIRAFF, especially for the high latency functions, which are the functions that can run closer to the cloud or even in the cloud. And we can see here that we managed to reduce the client spendings even up to 3 times for a certain kind of function. The story is a bit different for the low latency functions, which are set to run closer to the IoT layer, especially because, as you can see in blue and in green with GIRAFF and Edge Furthest, those are the only two placement algorithms that try to respect the latency, that actually respect the latency constraint, and thus it comes at a price. However, nothing is free, and we have to make compromise. So the biggest one for GIRAFF is that it actually has a bit of overhead before provisioning the function, which is simply the way we handle the auctioning and the chattering between the different fog nodes. And you can see that for high latency functions that can be executed in the cloud, for instance, we have to talk to more nodes to let them bid on the function. So it takes a bit more time. So in order to conclude, there are two main takeaways from this paper. The first one is that we introduce a reverse auction placement method for functional service in the fog that can end up reducing the client spending. And I still want to emphasize on this, which is that we respect strictly the SLAs that we accept and the functions that we run. And the other takeaway is that we make a large-scale test bed, which can end up running more than 100 nodes, and which can run more, but not in this paper. And that everything is pretty much reproducible, and you can run it on your own laptop if you want. Everything is on my GitHub. So now the ongoing work and the focus is a switch to being able to chain the functions, which is already done, and enabling more realistic workloads in the platform in order to be able to compare against state-of-the-art placement algorithms and measure other things. So thank you for listening to me. Do you have any questions?
Hey, thanks a lot. Some question from the audience? No? Have fast one? So a fast question from my side. So I understand that you provide these SLAs to deploy that, but all your experiments are in Grid 5000 with OpenFast. So here you are assuming that some functions are in the cloud and other in the edge, or how could you deploy that in a real setting?
Well, so Grid 5000 is only used to host all the VMs. Actually, every fog node is a VM that runs separated from each other. We interconnect them through the use of NetM to emulate latencies. Thus, we actually have everything that is pretty much like in real life, hopefully. And the idea is that for now, we are just pulling the functions from the registry, which is really just the same function, so it actually is optimized. But we are not really measuring nor actually focused on this part of the pipeline. So yeah, that's pretty much it.
Okay, thanks a lot. So we thank you again. Okay, and that's all for this session. So we in 10 minutes we go for the